Hi, Shadrach, are you able to hear us?
Hello.
Hi, we can hear you. Can you hear us?
Yes.
Excellent. And we've got your screen share.
uh, So is the screen more clear there?
Yeah, it looks okay.
Yeah, maybe you can just wait for 8 minutes for the time to, then we can start.
Yeah, let's start at 8:05-ish. Yeah, thanks.
So, hi everyone. I think you can start now. Maybe let me start by introducing myself. My name is Shadrach. Name is like Eric is on the first introduction for the slides. I'm based in Kigali, and I'm your TA for this for semester 2023. And today we'll be going through the recitation 5, which is talking about the basics for CNN and also the back propagation for CNN. Lara, can you hear me? So that I can make sure that everyone.
Yeah, we can hear you.
Excellent. So let's get started. So we can start by asking ourselves what is an image? An image, like as a human, we can present an image as a visual representation. That's how we say it. But the computer does not understand imaging in terms of visual. Remember that the computer talks in the terms of numbers. That's why we need to convert this visual image into the numbers so that the computer will be able to understand it. That's why we see the image in this representation. The image you can see the image like the matrix for different numbers, and the matrix is in 2 dimensions, which you can see the M like the height for the image, and also the N like the width for the image. And the numbers for at each index for these matrices, it is represented by the pixels at each index in the matrix. You can see this is our original image. We can see the different transformation that made so that can see each representation in the numbers. So at each cell or at index for this matrix, you have the numbers, which you call the pixels for the numbers. And remember that the pixels, I think already know that it is between 0 and 256, 255, if I remember correctly. Um, we can have the image in with different shapes or different channels. We can have the image with color channel, color channel, you know, that is RGB. We can have the image in black and white with 2 channels. We can have even the image with one channel. We mostly refer this to the gray scale image. So saying that they can have the 3 color channel, this kind of representing these color channels here. We can still have the blue, you have the green, and also have the red channel. And these arrows try to show the direction for each dimension. And also then we end up having the matrix for 3 dimensions. The first 3 represent the color channels. The second shape represent the height, and also the third represent the width for the image. And at each index for this image, we'll be having the pixels. It means that for each channel, we have different pixels. For each channel, we have the pixels representing the image. Now, so our focus is about the CNN. In the previous format, we've been using MLP, and MLP have seen that it's a neural network, but also CNN can say that it's a specialized neural network, which uses the convolution and the polling layers to extract features and also different patterns automatically from the input. So for MLP, we've been using linear layers as like the special component for MLP. But for CNN, we are not using linear layers. We are just using convolution layers and also polling layers. So the main focus for CNN is just for feature extraction. It does feature extractions. That's the main focus for the CNN. All right, so we can see the difference between the comparison between the MLP and also CNN. The MLP, we talk about the vector to vector. Remember that when you want to pass our input to the MLP, we need to flatten the input so that we can have one dimension vector. So if you are trying to process like 10 images or 32 images, 64 images, At the same time, that's what we refer to the batches. Then that will be having we'll be having two-dimension input because we're trying to do like one batch at a time, which have like 10 or 32 samples. But the features will be flattened so that we can have one dimension. That's why we're talking about the vector to vector. We'll be having the input to the MLP, which passes through the MLP, then the output will be the vector. That's why this can be the summary about the representation for MLP. So for CNN, now for the CNN, we just give the CNN the input, but also the output will be of the same shape, like the input. The, going back to the image, this is our image. This is the original image. Then after doing some transformation so that they can convert it to the numbers, we'll be having this matrix. And this matrix is what we refer to the features. The features. Those features, those different squares, that's what we are referring to, those numbers. The numbers we have here, the pixels for the image. Then for CNN, once we give this input to the CNN, we try to extract the best features from this original image, then which gives us the other feature map. That's why we say that for CNN, we do feature map to feature map. But for MLP, we do vector to vector. So that's the main difference between them about the representation for them. So we can look at the building blocks for the CNN. For MLP, I've mentioned that for MLP, the main component is for MLP, it is the linear layers. But for CNN, the main components of building blocks for the CNN is convolution layer and also the pooling layer. I have added the other part, which stays the others. The others, the reason why I say the others, the activation function, normalization layer, also linear layer norm, batch normalization or batch norm. Those other components can be found into MLP, but convolution and the pooling layer are specific for CNN, which is the main difference between with the MLP. But for CNN, we can build CNN by combining those main building blocks and also adding those additional others and the other parts which I didn't list here. So let's try to understand also the main of the hyperparameters for CNN. The CNN is made by the conv layer, the conversion layer as I mentioned. It has pooling layer and also the number of layers. Those are the main hyperparameters for CNN. Let's try to see one by one. For convolution layer, we have what you call the kernel or the filter. We have the sprite, we have the number of filters, also padding. The kernel, it's kind of like the filter. I say that the CNN is the main focus for CNN or the main process for CNN is for feature extraction. Then this kernel or the filter, it mentions the size of the kernel that we'll be using for convolving over the input image. The filter here, it is just a small matrix. The kernel is just a small matrix. And also the stride can be the step size for that kind of while we're convolving over the input image. The number of the filters will be equal to the number of the filters that will be applied at each convolution layer. The padding, we'll be looking to the padding, so the padding is, and also the pooling layer. For the pooling layer, we need to specify the pooling type and also the size, which we call the pool size. And also same for the pooling layer, we have the stride to be applied on the pooling layer, and also the number of the layers that our CNN architecture will be having. So let's try to see one by one. So convolution layer or conv layer, I've already mentioned, it is the core components of CNN. They apply convolution operation using linear filters or kernels to the input data. These filters can spread across input to detect the patterns, edges, or features. So, which is the main important for the CNN? Detect the patterns, edges, or features from the input. using those different filters. The kernel, as I mentioned, the kernel size of the convolution for the convolution kernels or filters determines the spatial extent over which convolution operation is applied. So the kernel, for the kernel size, this is the most recommended. We can go 3 by 3, 5 by 5, 9, 7 by 7. I don't know if you can go 9 by 9. So that's the further research you can make, or the other discussion that will be made during the class. The stride, as I mentioned, the more we take the bigger stride, the bigger stride, you understand you're making the bigger steps for the kernel when you're convolving. The padding, so the padding in CNN just it's using the convolution layer just to control the output size for the feature map. When we apply padding, we are trying to control what should be the output. Maybe we want the original input size to be equal to the final output size. That's when we use the padding. So for this, you need to use the appropriate padding so that we can be able to meet that requirement. Maybe if the input size will be equal to the output size. Well, so trying to see simply the convolution in action. So this is our input. This is our kernel. You can see our kernel for now it is a 3 by 3 matrix. This is a kernel of the filter. We need to convolve this filter over this input image. We are using the stride for one. So the output image, the output for after doing the convolution will be this one. But we want to see this step by step. Let's see. Let's suppose this is our input image. This one, we're going to use the stride of one. The kernel size is 2. It means that we have 2 by 2 kernel or the filter. We'll be adding the bias. The 0, 1, and define the value. Then remember that in MLP, we'll be during the forward propagation, we've been calculating the linear combination between the matrixing with the inputs with the weights. Then we add the device so that we can get the output. Then that output will be passed through the activation function and the other different techniques that we'll be using, like normalization and the other things. For this part, for this input, if we convolve this kernel, this filter to this input, then we add the bias, then we'll be getting the first item for our final feature map. This will be the output. Then this is the calculation here. How it is being done. Take A1 times AW, W11, then we add the summation. So this is simply the dot product between this portion for this image with this kernel. Then after that, we need to move, means the stride. You get here. The stride is this one, meaning we need to move our filter one column to the right. Then we apply the dot product between this portion for this image with this kernel or the filter. We add the bias with the corresponding bias. Then we'll be having the second element into the final feature map. This is the calculation for this. We move. We stride again means we move. We step by one because the strategy is one. We do the same calculation. Then we get the third item to the final feature. After that, from here, we see we are done with this. Then we need to move down by the stride value we have or the step size. You can see that we have moved down by one row. For this, we apply the dot product between this portion for this image with the filter. Then we add the bias, then get the final output. We continue the process until we finish all the parts for the image, means convolving, striding over the input using this filter. You can see that the filter is fixed. The filter is constant, if I can say. For each convolution, for each convolution layer, the filter, it is fixed. the value for this filter. We continue the action until we go to the final output. You can see that our final feature map, it is smaller than the original input size. Feel free to ask the questions either in the chat or also if it can stop me. That's okay.
I have a
So,
question.
okay, okay.
Yes, so is it always normal that the feature map, like what you get in the output, is smaller than the input in terms of the size?
Yeah, yes, it is true. As long as you try to maintain it so that it can be the same using the padding technique, we see that.
Okay, so if you use the padding, so the use of the padding is to get the same size as the input, right?
Yes.
And does it have any advantage?
Yeah, that's kind of experiments you need to make on your own to try to see if I apply this padding, what will be the output. Because I cannot say that if I apply the padding, that will be the best way to extract the features. That's kind of like different techniques to use, like the parameters to be used so that we can control what will happen if I do this.
All right, thank you.
Welcome. So let's go to see how we can make the calculation for this output size. So we can see the original image size, so this, then the output will be this one. So this is how we do calculation for this output. Here it is written output width. I'm supposing that we have the 2D dimension for the image 2D. Means we have the height and also the width for the image. But if you have like let me say the time series data, we'll be having like all like the other data. That's where we need to consider one dimension data, which have one dimension data. I think you hear that. We can say the output size. But for the image, we need to make the calculation for the height and also the calculation for the width. So how do we do that? We just take the original input size minus the kernel size, means the width for the kernel. This one, this one. So means this is the height, this is the width for the kernel, this is the width for the original input. Then you add 2 times the padding, means, for example, if I need to pad with 1 0 left and right, that's why you do multiplication by 2, means from left and also the right. That's why this 2 is coming from when you do calculation for the width. Then after that, divide by the stride. The stride. Then can I see if I can write? I'm saying, I don't know if you can, let me see. The width minus the kernel plus 2p divided by the stride, then plus 1. I think this is more clear. Ignore this. This will be how we'll be calculating the size, then you put the output size for the width. Taking the width, original width for the input size minus the kernel size plus 2 times the padding size divided by S. Means the stride. This is stride. Then for the height, you do the same. The height will be equal to kernel size. Mostly kernel size is like mostly kernel is a square. Then plus 2p we divide by the stride, then plus 1. This is how we'll be doing this final output, this one. That's how we get the final output for this one. So for example, we can maybe try to see we can try to see if we how this is done. For example, this we have 1, 2, 3, 4. 1, 2, 3, 4. We have 4. Sorry. We have 4 by 4 input. Then if we, for example, let me do for 4. 4 minus k, which is 2, divided by 1 plus 0. Because the padding is 0 for now. We didn't apply any padding. Then plus 1. Plus 1. 22 minus 2 is 2. Divided by 1 is 2, C2, then plus 1. Now the final will be 3 by 3. That's how we did the calculation for this output. Okay, let's go next. Yeah, so if we apply padding, this is what I was saying there. The padding height was 0, and so the spread is 1. That's why we got this value. So I'm try to this. Okay, so the next that we can see then how this is being done. So let's suppose this is the image we have here. We need to pass this image into the convolution layer. This is our kernels. So practically, sorry. This is our convolution layer. Then practically, this convolution layer, there's four neurons which are there. Those will be the output. That will be the output channels for this convolution layer. Then for each layer, we can see we have 3 kernels or filters. But for each filter, we have 3 matrices. Why? Because this image, it has 3 channels. It is RGB. It is an RGB image. Then that's why for each kernel, we have 3 matrices. One for R, G, and B. Then we do it across the 4 output channels. That's why we have the matrices which are stacked in this way. Then we apply the alpha after finding our Z. This is our Z. This is our Z here. Those different Z values. We apply the activation after this. Then this will be the output channels we'll be having. We'll be having 1 after applying those stuff. We get this. We get the image in the model will be having this image, the features which looks like this. Then before which can be then passed to the next convolution layer or max pooling layer. Yeah, this is same like the before what we presented before. But let's see how this for the strategy 2. For example, if I have the strategy 2, the same image, the kernel is the same. But for this one, you can see that because the strategy 2, this will be moving 2 columns. If I'm going left to right, 2 columns. Then I move down 2 rows, then I confirm the process. You can see that the shape has already reduced to 2 by 2. But previously, because the slide it was 1, we had 3 by 3 as the output size. You can see that when you increase the stride, now we are trying to decrease the output feature map. Let's see. What do we see when we see the stride which is greater than 1, and also the stride which is less than 1, and also the stride which is equal to 1. When we have the stride which is equal to 1, this was the case. It means that the sprite, the output for the sprite is not, so the for the feature map, the output, the size of the output feature map is not being affected by the sprite, if you can say. But if the sprite is less than, if it is less than 1, from the formula, we have seen from the formula, we have seen that, for example, if I do this plus 2p over the sprite plus 1, you see, if the sprite it is less than 1, this formula will look like this. P times, maybe, for example, the sprite is 0.5, will be times, let me say, the ternary division, 5 over 3 will be like 5 over 5 times 10, like this. You can see that the form will be kind of changing because the sprite is becoming the decimal number. Now it means that the size for the output, it will increase. That's why we say it here. Think about how this is related to upsampling. Means upsampling, we are trying to increase the size for the image before. Then if the sprite, it is greater than 1, think about this, which is for this band. If the sprite is greater than 1, this is what you have. You see, the size of the image, the input, is being reduced. So that's why think about this in terms of downsampling, which is already being implemented in homework 2, part 1. This is when the sprite output is 1. This will be was the output. If it drops some intermediate, means that the sprite output or sprite will equal to 2 will be having the final shape, which is 2 by 2. Then think about this, the different scenarios in terms of upsampling and also downsampling, how they are related to the convolution with the sprite one. Okay, padding. We talk about padding. We say padding, for example, if we need to maintain the output for the feature map, that's when we try to apply the padding. The padding means we need to add, for example, for this image, I need to add, for example, zeros here. For example, zeros here, before I apply some kind of the convolution to it. In this case, the padding will be equal to 1. For example, which is being applied for different shapes of the image, left and right, means the height and width. For example, if the padding is equal to 2, means I'll be applying 2 zeros here, zeros, 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 here, this one, before convolving. Then this will be the final step for the input after applying the padding to this. Then after applying the padding, then I can apply the convolution to this input image. You understand that it will affect the output for the feature map. Sebastian, did you see that in terms of padding?
Yes, I did.
Yeah, great. So this is what padding does. It is supposed to try to maintain the output for the feature map. Okay, so the next thing we need to touch on is about this padding. This is padding, what I was explaining there. You need first to surround the original input, the input image. Then you try to transfer with some zeros to it so that you can maintain the final output for the image. Then if you apply it, you can see how the output size has increased compared to the previous one, compared to the previous one. Okay, so then let's talk about multi-channel CNN. For the RGB images, this will be our input channels, which have the red channel, the green channel, also sorry, the red, the green, and also the blue. Then we apply our CNN convolution layer. This will be our output channels. What does it mean? This output channel, for example, if you have the convolution layer, which have the input channels, which is equal to 3, and also the output channel, which is equal to 64. Those 64, that's what I'm referring to, the output channels from the CNN convolution layer. See, here we say that each kernel of the filter has many channels as the input does. What does it mean? For example, if the channel has the kernel channels, we refer to them to the input channels. But the filter channels, we refer them to the output channels that the convolution line will be producing as the output. Then if channel C for the kernel convolve with the channel C to corresponding input. For example, let me go back to this. This is our input channels for the particular image. This is our kernel. Then the matrix multiplication or the operation that will be applied between the input and the kernel, it will be applied for each channel with its corresponding input. It means if it is red here, the multiplication operation will be applied to its relative to the corresponding kernel here. That's the meaning. Then afterward, we'll be having the 3 feature maps, right? Then after that, we need to do summation for those 3 different feature maps so that we can have the final output to this, which corresponding to the one output channel, or what we call the filters channels. Here, how we can try to illustrate this. We have 3 input channel. We have 1 filter or 1 kernel. Means we'll be having 1 output here, right? So we have these 3 channels that will be mapped to, we'll be having the multiplication, matrix multiplications here to this. Then after this, we'll be producing like three maps for each respective channel. Then after this, we do the summation to produce the final output map. Why? Because we only have 3 filters. Sorry, 1 filter. This means that we'll be having only 1 output channel. That's why you have 1 output map, the feature map.
I have a question on the previous slide.
Yes.
So the addition, is it element wise?
The addition between when you are convolving the multiplication is the element wise. Then after you apply the summation.
No, so I mean for the 3 almost output maps, the Z. Yeah, that one.
Here.
Yes, the 3 channels. So yes, so when you're putting them together, are you adding them element wise?
No, yeah, element by element, but so that you can get the final output like 1. Is that what you mean?
So okay, so how do you add them? How do you add the 3 output maps?
Okay, so let me suppose I have ZB11, right? For blue. Then I have a green, I have the ZG11, right? And also have ZR11. Then I add them, right?
Oh, so it's element wise.
It's an element wise, but at the end, you can see it's an element wise for this one. At the end, that will be having only one map, which correspond to those.
All right, thank you.
Did I answer the question?
Yes, thank you.
Great. Yeah, so if you have 2 two kernels, means we'll be having two output maps. Means two kernels, two filters. You can see this, the first one will be applied to all those three channels here. The output, then we get the output map. The second one will also be applied to all those three input channels, then get the final output map. Then we'll be having two output maps. So in terms of the implementation in practice with PyTorch, when you see the input channels, that's what we're referring to. Sorry, this one. When you see the output channels, that's what we're referring to. There's a two which are here. It will be equal to the number of the kernels that will be applied into the multiplication operations. Okay, so the pooling layer. The pooling layer, it's one of the fundamental components for convolution neural network. But the main purpose for the pooling layer, it is to reduce the size for the input, right? But also still maintaining. So it's a try to look for what can be the best features we can use instead of considering all the features. So try to check what the best candidate features, then try to pull them together so that you can try to even reduce the computation cost because you're trying to reduce the size for the image. So that's what say the pooling layers are responsible for reducing the size of the feature maps while retaining the most important information from the input. So for pooling layer, we have the max pooling and also average pooling. That's what we have here. Let's try to see how max pooling layer works. Let's suppose this is our input. Then you have our kernel. Remember that I told you that the pooling layer, the parameters for pooling layer to the stride and also the kernel, or the pool size or the pool. Let's suppose that our pool size or the kernel or the filter for the max pooling layer, it is 2 by 2. We applied the convolution how we did, but for this time, it is not a convolution. We just check the portion for the input. That's what we call the pool size. I was referring to the kernel so that I can try to tell you how we go through the image. But here for the pooling layer does not have the filter because this is not a filter. But what we just call it a pool or the pool size. Let's have the pool size, the 2 by 2. I take the portion for this image, which is 2 by 2. Then I try to look for this small matrix. I try to see the maximum value in this matrix. Then I put it here. For this case, we have 16. I move with the stride of 2. I think you're already familiar with the stride. Means I will jump to columns 1, 2. Then I move here. I check this matrix. I just look for the maximum. You can see that we just flatten this matrix. We are not saying that we just saying that, for example, in the first row, second column, that's where there's a maximum. The second row, the first column, that's where we have the maximum. No, we are flattening this. Then we try to know which is the maximum between all those values for the bar. Then here we get 9. We move down 2 by 2 because the strat is 2. We get 67, sorry. We move to the right to get 13. So this will be the final output from the max pooling layer. Then it is the same the calculation for the output for the output size. For example, for the height, it is same as for what we did on the convolution. Minus the pool size. This is the pool, quite cool. We divide by the stride, we add 1. For pooling layer, we don't have the value. We don't have padding for pooling layer because the pooling layer is just supposed to reduce the size of the image while we try to retain the most important information from the image. That's why we don't use the padding here. So that's how you calculate the size for the final output size for the max pooling layer. So yeah.
I have a question.
Yes.
Right. So far you've demonstrated two things, right? We have the input image, and then there's a kernel, and then the output. And this time we are seeing the input, we are seeing the pooling layer, and then the output. So my question is the pooling layer replacing where you have the kernel filter or the kernel? I don't know if my question is clear.
Yeah, so I said that for the pooling layer, we don't have the kernel. It's just a pool size.
Okay, so which means where we have the pooling layer, we don't have the kernel.
Yeah, it's not a kernel. We just call it a pool size because the kernel will be contributing to the parameters for the network. And the max pooling layer, we don't have the parameters for in the pooling layer. You get that?
I'm a little bit confused. So which means that
So I'm saying
when we have the pooling layer, it is replacing the kernel. Is that right?
yeah. Oh, okay. So for the pooling layer, just take for the convolution layer. We have what we call the filters or the filters or the kernels, right? Yes. Then
Come
for the
again.
pooling layer, I'm saying that for convolution layer, we just have the kernels or the filters.
That's right.
Then we just refer to the kernel size or the filter size, right? But for the pooling layers, we don't have the kernels because the kernels contribute to the parameters for the network. But for the pooling layers, we don't have the parameters here. We're just saying the pooling, that's why we're saying the pool size. The pool size just take it like a matrix, like the size of the matrix to be considered. Why when we are trying to calculate the maximum. The portion for the input, for the
Okay, so my question is, okay, so then my question is, is the pooling layer getting its input from the output of the convolution layer?
Oh, so I see. Yeah, you're right. That's correct. You can apply the max pooling layer to the output for the convolution layer. That's how you do that.
Okay. Okay, that was what I wanted to understand. Thank you.
And great. So if understand the max pooling layer, the average pooling layer, we just replace the max with the average. You just look at the average between for each question for the matrix you're looking at. That's what the difference. So this is the end for the CNN basics. We are going to look to the part for the back propagation. But if you still have a question about the first part, please feel free to write into the chat or be respond to the questions. Or if you have it now, we can feel free to ask before we move back to the back propagation. Is there any question before we proceed?
There's a question.
I have a question. So, like, you said you combined the three channels into one, but then, like, is that like just for like one, like, what do we like? But we like repeat the like striding and filters and everything. So after that point, will it always be one channel left?
You mean this?
It was like a little bit before. I think this one, yeah.
Can you repeat the question?
Yeah, like, so once we go from channels to one channel, but we still repeat the like filtering process and like for more layers, right? So like, are we just always going to have one map from that point on?
Oh, I see. So, what we mean here, this output map, you'll be just indicating this in the convolution layer during the implementation. But the operation how it is being done here, this is our input channels, three input channels. Let me just consider this green, the green channels here. Then I'll take this green channel, then I apply this kernel. This kernel will be applied to this green, but also to be applied to the green will be applied to the corresponding green for the kernel. We go for the red also. It will be applied to each corresponding red here. Then after, since we have one filter or one kernel, it means that we need only one output feature map. That's the meaning. If we have two kernels here, it means that we'll be having two output feature map.
Oh, so this is like
Does it answer your question?
there are like multiple ways to
Mhm.
do it, so you can use as many filters as you want. So in this case, we only use
Yes.
one. Okay, okay.
Yes, you can have many filters, as many as you want. These are just a kind of the parameters that we'll be
Oh,
defining.
okay, thank you.
Yeah.
Yeah.
Welcome.
Yeah, I'm just wondering, do we always add the three like intermediate maps, or is there a case where we would keep all three when moving to the next layer, like separate?
So you mean for the input?
No, I mean for the output. Do we always add it into and combine the three into one output map, or is there a case where we would keep them separate when moving on to the next step?
Okay, so let me give you an example to the MLP. You remember how we do for linear layers? We have the linear layer which have like 2 as an input, then you get 4 as the output. Then the next one to be getting the output as the input to the next layer. Do you remember that?
Yes. Yeah.
This is the same logic here. If you have the first convolution layer, which have like a 3 as an input channel, right? Then the output channel means the filters will be like 32. If you move to the next convolution layer, the input will be 32, then will be its corresponding output, based on your kind of the decision you make to the output to that second convolution layer. But you don't have saying the contrary to this. This does it immediately to this. For example, if you have the input channels, 3 input channels here, so the output channel, I said that this will be having it will be having its corresponding to, for example, if I have like I have three channels here. Each channel here, it will be multiplied by those three channels here. Because each channel here, it will be having 3 input channels. That's why the multiplication or the summation between with the matrices between the 3 channels with its corresponding channel here will be then across 3 channels. It means each filter will be applied to 3 input channels. Look at here for this part maybe. Look at this. We have 2 filters here. This filter will be applied across the 3 channels here. Because this filter, it will be having 3 channels in it as a representation, how we're presenting it here. Then after this operation, which this will give us the output feature map. Then the second filter, it will do the same operation to those 3 channels. Then it will give us the output feature map, which finally get to feature maps. Does it answer your question?
Wait, sorry. I think I was more asking, like, I understand that the number of filters corresponds to the number of inputs. I was more asking, like, in terms of the output, do we always flatten it into like we add it through the three
Oh, okay. I think
maps?
I got it. Shada, can you go back like one slide, the previous one? Oh, you are asking why should we always add from here to here, right?
Yeah, or is it a case where we keep them separate for the next
Right.
step?
So general convolution layers, or what you call as con 1D, con 2D, con 3D in Torch, these will always get added. However, there is something that is called as depthwise convolutions, in which you will be retaining all of these maps, but that's not the usual convention. The usual convention, when you apply a convolution operation or a con layer, these would get added.
I see. So then, and then also in this case, I guess, since we, okay, so on the left, very left, I know we have three inputs, so three channels, so we have three like filters. And then now we only have one output map. So does that mean in the next step, we would only have one filter? Because that's like the output equals the input.
No, so here's the thing to keep in mind. The number of channels in the filter is equal to the number of channels in the input.
Right.
So for a 3-channel input, every filter would have 3 channels.
Right, yeah.
You can have multiple filters acting on the same image. Shara, can you go to the next slide? Yeah. So you can have two kernels applying on the same image. If the number of kernels or the number of filters that you use is equal to the number of channels in your output. So if you are using 2 kernels, your output will have 2 channels, and the input to the next layer will have 2 channels as input.
I see. So then, for example, in this example, in my next like step, each of the boxes, like the purple and red, would have two like stacks.
No, yeah, like purple and red would be stacked together. So it would have 2 channels. Like purple is only 1 channel, red is 1 channel. You stack them as input for next layer.
I see. Yeah, that makes
So you have like blue, green, and red stacked together, right?
Yeah.
So we are just splitting them to show the output for like separate kernels. But once you have this, you stack them, and then that acts as your input for your next channel.
I see. Yeah, that makes sense. Thank you.
Yeah.
So just to clarify, we take something that's like a red, green, and blue channel, and we turn those channels into feature channels, essentially, where this purple one and the orange one are no longer red, green, blue, but they represent something else.
Exactly. Exactly. So let's say you have a sequence of convolutional layers. So you had sequence of linear layers, right? And at the end, you got a representation, of it from the linear layers from the input. In the same way, when you have, let's say, multiple conv layers, this will be like passed again to the next layer and so on. And whatever you receive in the end is like a representation of the input. Right. Any other questions before this part, before we move on to backpropagation? Okay, I think we are good. Thanks, Shadrach,
Yeah, I have
for
a question.
doing the recitation. Oh, yeah.
Yeah, what makes the kernels different? Since if they are all the same, then if the first kernel, the purple one, for instance, if it moves across the 3 channels, and then the second kernel, if they are all the same, wouldn't they all produce the same output? What makes them different?
No, they will have different outputs. The weights are not same here, right? W1B11 and W2B11 are not same. So they will be different outputs. The purple and red one are not the same.
Yeah, I mean, what makes them different? Since I'm assuming it's the same code that initializes the weights.
Right. So
Uh,
if you initialize weights randomly, then that's what introduces difference in the first place. And then when you do backpropagation and all the weights get updated. So it's the weights of the kernel that makes the difference from the input to the output.
Okay, thank you.
thank you, guys. I think we can go to the second part for the recitation. So I think you can present your screen, right?
You can I can present from here. You can stop sharing, I guess.
Okay, thank you.
Okay, so we will now look at backpropagation in CNNs. This is something not covered in the class till now. It will be covered next week. So I'll go slow. So feel free to interrupt if you don't understand what's happening here. So just a quick overview of backpropagation. We we tend to draw the computation graph or the influence diagram. We see what are our inputs, and then let's say q is equal to x plus y, and then f is equal to q into z, and we for given values of x, y, and z, we have f basically. Now, when we try to do backpropagation, we try to compute the derivatives by going back. So let's say df by dq, I mean like partial derivatives df by dq is just z. You can also look at the equation, or you can look at the computation graph. And we can like compute all the derivatives and then flow backwards. This is how the general chain rule of backpropagation, chain rule of derivatives work. So again, so this is just like a refresher of how we can compute df by dx, which is basically df by dq. So f is q into z, and then q is x plus y. So you can do df by dq into dq by dx. This is how we do the chain rule. So now we have a convolutional layer, right? So this is basically how we will be representing a convolution. So x and y will be the inputs. Our function f is actually will be the convolution function, and z is actually the output that the convolution gives. The x and y, what do you think would be the inputs to the convolutional layer? Like inputs as in, what do you think are the inputs of convolution function f that will give me the output? What are the two things that we are using? Yeah.
You need the channels from the previous layer,
Right.
and then you need all the filters and stuff.
Exactly. So we have one will be the input from the previous layer, or just the input, initial input, whatever it is, and then one will be the weights or weights of the kernel or the filter that we have. So this is just okay. So this is just how we will be like computing derivatives and so on. So yeah, let's come to the actual example of convolution. We have our input x, we have our filter f, which is the kernel. We convolve, and then we get an output. You can see the shapes, like it's this 3 cross 3 and 2 cross 2, and we will get a 2 cross 2 output, right? All the elements are marked, let's say like using indexing like 1 1 1 2 2 1 and 2 2 and so on. So this is the convolution operation that's happening here. As you can see in the top left, the filter moves across the image or the input x, and we actually get the values of 011, 012, and so on. So you can look at how the multiplication is happening, and then we add it to get the output of the convolution operation, right? Again, I told you, yeah, so if you look at the computation graph, we have the input x, we have the filter f, we have the convolution operation, and then we have the output. We want to compute, so let's say we have the derivative of the loss with respect to the output O. Let's say we get it from when you're doing the backpropagation, and now we want to go backwards. We want to compute the derivative of the loss with respect to x and the derivative of the loss with respect to f. We need to compute the derivative for both of these, like both x and f, because if dl by df would be used to update the weights of the filter. This is basically the update rule that we have. We have the weights, and then this alpha is the learning rate. We have the derivative that we have computed. Like let's say we have that value, and then we get our updated weights for the filter. Similarly, when we compute the derivative of the loss to the input of the convolution, that will serve as the derivative of loss with respect to the output for the previous layer. So when we need to go back, if you remember for the linear layers, we used to compute it with respect to the weights w, and we were computed with respect to x, and we would do the backpropagation to the previous layers and so on. The same case is happening here. Only the function, instead of it being a linear function, it's now a convolution. The rest, all of the stuff stays the same. So let's look at how we can find the derivative of the loss with respect to f. This is used to update the weights of the filter that we have. So let's say the output, let's say when we do this, if you look at these equations, if I place the filter on top left corner, I have O11, which is X11, F11, and then 12, 21, and 22, and so on, as you can see in the equation. I'm using the same equation where the output 11 is equal to the product, and then we sum it, and then that gives us the output. So when I try to compute a derivative with respect to f, I have 4 values of f. Our filter was 2 cross 2, so I have 4 weights in my filter or kernel, and I can compute the derivatives. So this is just a very basic linear equation. So when I do the derivatives, just x11, x12, and so on, as you can see. I think this should be pretty clear. Like, this is a very simple equation. Now comes the part where we try to find the derivatives of the loss with respect to f11, f12, f21, and f22. Remember, we have 4 parameters in our filter. We need to compute the derivative of each parameter of the filter with respect to the loss so that I can update the corresponding parameter with its corresponding derivative. I'll just go back quickly. So if you look at these equations, f11 comes in 4 of these equations, if you can look. So the f11 weight acts on x11, x12, x21, and x22. And we have 4 outputs based on that. This is precisely why we have 4 terms in dl by df11, which is basically f11 interacts with the output O11, O12, O21, and O22. Probably, like, if you can look at these slides to deeply understand, but this is basically how we write the chain rule. So if you draw the influence diagram, O11, 12, 21, and 22 influence F11, and then F11 influences loss. So when you try to compute, it's just a chain rule that we are doing again. So now I have the derivatives of dl with F11, 12, 21, and 22. I have the derivatives with respect to all the parameters that is present in my filter. Let's fill in some values. We know O11, the equation of O11, right? And we know we can compute what is the derivative of O11 with F11, which is basically X11 if you can look from here. Derivative of O11 with F11 should be X11. I just plug in those values here. So we will get dl by do11, which is the loss, the derivative of the loss with respect to the output. We will get it from the previous layer. We'll get it from the layer that we are previous, as in the next layer, but then when you're backprop, it's reversed. So yeah, it's sorry. So we have the derivatives with respect to the outputs, and then I have a formula that can compute the derivatives with respect to the weights f in my filter. Does these formulas look like they follow a pattern? Like, if you can just look at one of the equations, it's you can just look O11, O12, O21, and O22 is there. And then you can see the multipliers are like x22, x23, x32, and x33. Similarly for all the equations. Do we see some sort of a pattern here? Let's look at the equations of convolution that we had. When we are doing the simple convolution operation, we also have x terms represented like this, like 1, 1, and then f, the weights f represented as like this. So let's look at the first equation. Notice the indexes are like 1, 1, 1, 2, 2, 1, and 2, 2, right? Now, when I look at the equation of the derivative of loss with respect to f11, we see that the indices that are followed, the indices that are written is 1, 1, 1, 2, 2, 1, and 2, 2. It follows a pattern that we have seen. This is basically a convolution, right? We were doing a convolution on the inputs, and let's assume like dl by d O11 was like f11 for like just now. We can see that equation exactly matches what we had. So instead of the filter weight f, now we have dl by d O11, O12, O21, and O22. The x parameter stays the same. So this is basically the derivative of the loss with respect to the filter weights f is actually a convolution between the input x and the derivative of the loss with respect to the output of that layer. Because if you look at this image, if you convolve this this filter, which is the derivatives filter, with your x input, you would see that if we place it on top right, we would get the exact same equation as the first one here. You can similarly work that out, but these equations would actually correspond to the convolution operation that we have. So what do we get here? That the back propagation can also be done using a convolution operation. This is something that is very helpful in if you are doing 2.1, because you don't have to write much code. You just have to change the variable name, and then you can reuse your forward method to do the back propagation method. So for the derivative of the loss with respect to the filters f, it is a convolution between the inputs and the derivative of the loss with respect to the output of that layer. So now we know how to compute the derivative with respect to the filter, and this will be used to update the weights of my network, weights of the convolution layer. Now let's look at the derivative of the loss with respect. I think it should be derivative of the outputs with respect to x. I think, sorry, not finding dl by do. It should be like dl by dx. So we have the same equation, O11 is equal to the same equation that we had. When we are trying to differentiate with respect to x11, 12, 21, and 22, we get the, you can see that we get f11, 12, and so on as our outputs, right? And in the same way, I try to write the derivatives of my loss for each of the input that I had. In the linear layer, in case of a linear layer, we do it the same way. We try to compute a derivative for each parameter. The only thing here is the input is in form of a matrix, so you have x21, 22, 23, and so on. So you can compute the derivative of the loss with respect to the input x based from the derivative of the loss with respect to the output. And so keep these equations in mind. The reason being, let's say I have my original filter, which was f11, 12, 21, and 22, right? Let's try to rotate the filter by 180 degrees. Basically, let's say I flip the filter vertically. So when I flip the filter, F21 and F12 and F11 will get interchanged, which is as shown here, and then F22 and F21 is interchanged from here. So it's basically a flip on vertical, and then I flip it horizontally to rotate this matrix by 180. It's basically I'm rotating it by 180 degrees. You can also do it by flips. Doing it by flips makes it easier on NumPy, but yeah, that's why we are trying to represent them as flips. So when you do the flip, you rotate the initial filter that you had, and then let's say we get this filter. Why we are doing this is something that probably in Monday's class you will try to identify. But let's say we do this, right? And let's say we have the filter f. We have the loss gradient, which is derivative of the loss with respect to the output. And let's say I do a convolution here. Keep in mind this convolution is happening with a padding, because you can see the filter is actually going out of this is your input. So your filter is going outside of your inputs, right? So this is actually happening with a padding. So as you can look, when the equations that come in, let's say dl by dx1, 2, and so on, this is computed based on a convolution with your filter rotated 180 degrees and your gradient padded with zeros that can support this convolution. So you can actually get the derivative of the loss with respect to your input as a convolution between your filter f and the loss gradient, which is dl by do. Okay, so any questions here? So we can compute the derivative of the loss with respect to the filter weights f and the input x just by using convolutions. Yeah.
From the animation, it seems like we're starting now from bottom right as the.
Yeah, actually I think the filter should move and the input should stay the same. But yeah, think of this as if f was your input. So I think I explained it in the reverse manner. F is your, since the equation is like f is your input and the loss gradient is what you're convolving with, the f stays constant, that's the input, and you convolve using this as your filter, and then the filter moves like across f. And f is padded with zeros, one column on left and right and top and bottom. That's why these derivatives would be zero, for example. where the filter is going out of the input, the derivatives will be 0.
And the indices for x start at the bottom, right? So computation. Okay.
No, it's because the animation is reversed because we are starting with F11. That's it. F11 is there. That's why we are trying to so that the equations are in line. That's the only reason why the animation is reversed. But again, you can do the convolution from top to bottom or bottom to top. It doesn't matter. You would get the same output when you do the convolution. Yeah.
Why is it called full convolution? Is it like a different operation than the convolution we saw before?
It's the same operation. So we have our input vector x, we have our kernel or filter f, and what do I mean by convolution? Convolution is just basically placing that filter on your input and then sliding it through. And while we are sliding, we compute the product and then add it to get like the final value. So that operation. So basically, so this equation where O11 is equal to the whole sum, this is basically the convolution that's happening, right? So
But
yeah.
is it different from, like, is full convolution different than just plain convolution?
No. It's not different. Where did you see full convolution? Oh, it's just to imply that we are doing a padding here, and then you can look at the filter, right? It's going out of your input, right? When we initially do convolutions, it doesn't usually go out of the input. The padding was 0. So we are just doing this kind of a convolution to so this is a case where you will always need to pad to get your final output, which is this. So that's why wherever the filter goes out of the input f, you would have a 0 padding there, and then that multiplication is basically 0. You can also look at the equation that's coming along. So only we have one term here. We would have two terms now, and then we would again have only one term. The rest of the three are 0.
So like in this example,
Okay.
it would be like the filter f with padding of 1, right?
Yes, with padding of 1.
Okay.
So a padding of 1 actually, even in torch, if you specify padding as 1, it is basically padding on the left, right, top, and bottom. So you would have 2 rows of 1 and then 2 columns of, 2 rows of 0 and 2 columns of 0 surrounding your input. This is also why we do minus 2 times padding when we try to compute the shape of the output of the convolution layer as well.
Thank you.
Why do we flip the filter?
Yeah.
Yeah, why do we flip the filter? Or why did we do the 180-degree flip?
I can't hear you properly. Can you speak up a little bit?
Why did we do the 180 degrees flip of the
Right,
filter?
right. So there are two reasons. Like I can give you two explanations. First, if you just try this out, this would work. But that's not the obvious explanation. I think you should wait for Monday's class to figure out why we are trying to rotate the filter by 180 degrees. Prof will explain this in class. But this is just for you to explain so that you guys can start early on the homework, and then I'm just explaining how this derivatives work. But obviously wait for Monday's class. I think you'll understand why we are trying to do why we are flipping rotating the filter by 180 degrees for this convolution.
Okay.
Yeah, so in a nutshell, it's basically we observe that when we are doing the forward and backward, you'd observe there are animations in prof slide that you'll observe that will show you that yes, if we rotate the matrix by like 180 degrees, it will do a full we can do a convolution and get the derivatives. So this is the final nutshell that you have. This is just sufficient if you want to just get done with your homework, but please try to understand why convolution operation happens when we are trying to do the backpropagation. We have listed out all the equations in the recitation slides, so that might help if you want to do the calculations by hand and then figure out, yes, the convolution is actually what it works.
Are these slides on the website?
Yeah, we will be updating the slides as well as the recording of this recitation on the website as well as on Piazza. Yeah.
Okay. I have a question.
I saw that in like homework, it says it's scalar. Is there any like
Yes. So if you remember, bias is just a scalar value, right? So it's the same as that can happen in a linear layer as well. It's in the very same way that you update the bias there. You update the same way here. The important stuff is updating the weight parameters, because your weights are in a matrix. You would only have one bias for one filter. So that would be like, so if you write down the equation, it would be you convolve plus b equal to your output, and then the output by the bias, the derivative is 1, so you can just subtract and do all that stuff.
I have a question.
Yeah.
What's the difference between a convolution and full convolution?
Right. So the full convolution is basically this that's happening. This is just trying to emphasize that you are trying to convolve with your filter, that is the loss gradient, on your input, that is the filter f, where you go outside your inputs as well. So you try to convolve every element of your filter, every element of your loss gradient with the filter. That's why this is called a full convolution, because you are trying to go outside of your input so that you can convolve every element of the loss gradient with every value in your filter. That's the reason why it's called a full convolution. But if you
Okay.
just think of full convolution as convolution with padding, that's the exact same thing.
Okay, so does it mean in the assignment, the homework part 2, we are always doing a full convolution because all the layers have padding? So, or
So
the suggested architecture, all the layers have padding.
no, so I think there you just call the torch con layers, and then that should work. This is specifically for the case of back propagation where you are using full convolution. In the case of the homework where you want to do full convolutions, you can define padding, and it's not always the case that the padding will be 1. It's just for this case that we have padding 1, because look at the output shape and look at the input shapes that we have. Based on this, you can calculate the padding value, right? You know the equation that goes from the width of the input, you can take the stride, padding, and the width of the kernel, and then that would give you the width of the output. So if you try to find out the value of p, given you have all of the values, that's the length by which you pad. So in part 2, if you want to do a full convolution, you can pad your input appropriately, that will, so that based on your kernel size, so that full convolution happens there. But this is not a necessity for like homework 2, part 2. You can either use convolutions or full convolutions. It really, like, I don't know if it makes much of a difference, but yeah, this is something that you can try out in ablations. So I think that's all I had for backpropagation. Hope you guys understood. I knew I did it before the profs class, but yeah, and also we are on time. So any questions?
I have a question.
Okay.
So is there any sort of back propagation
Can you probably ask this on Piazza? I think we are up on time, so I'm sorry for that. But can you probably ask this on Piazza?
Okay.
I'll put a post for Recitation 5. You can ask it there, or probably just make another post. Thank you, everyone. Thanks for attending the recitation.